Hey there, everyone. We are in the middle of chapter 632, more elimination. So we're talking about more ways that we can use the elimination method to solve especially word problems. So in lesson 631, you learned how to use the elimination method to solve systems of equations. And in this method, you combine two equations in a way that eliminated one of the variables. This method is particularly useful for solving systems of equations where both equations are in standard form. Dragonflies and fairies. Phoebe was helping her mom buy gifts for her little sister's birthday party. There were 11 friends attending the party. Dragonfly wings for the boys cost $1, while fairy wings for the girls cost $2. And you know what? I really don't care if it has to do with boys or girls. It really doesn't matter. Phoebe's mom spent $18 on the gifts. How many dragonfly wings and fairy wings did Phoebe's mom purchase? Use the elimination method. So first we're going to have that the number of dragonfly wings plus the number of fairy wings equals 11, because it says that there were 11 friends attending the party. So if we add up the sets of wings, they have to add up to 11. So the first equation has to do with number of sets of wings. The next equation is going to be cost. So it's $1 per dragonfly set plus $2 per fairy set, and that has to equal $18. So again, when we're setting these equations up, first equation that I wrote has to do with number of pairs of wings. Second equation has to do with cost. So there's always going to be one equation for one type of scenario. So the first scenario was the 11 friends, so total people. Second scenario was total cost of the gifts. If we want to try to solve these, you'll notice that I have one D on the top and one D on the bottom, but they've got the same sign, right? They're both positive. So if I do D plus F equals 11 and I take away D plus 2F equals 18, I could either multiply the second equation by -1 or I can just subtract it. So D take away T is gone. F take away 2F is -2F. 11 take away 18 is -7. And that F take away 2F should just be -1F, not -2F. And divide by -1, divide by -1, F equals 7. So that tells us the number of fairy wings. So 7 fairy wings. And we would have to go back and say, okay, if we plug that into one of the original equations, D equals 4. And 4 dragonfly wings. All right, so not terribly difficult as long as you keep the two types of equations separate. Rachel's trying to solve this system, combine these equations. So right now we've got 2x, 3x, plus y, minus 2y. None of those cancel the way they are. If we try to do that straight up and we just combine them, we get 5x minus y equals 11. And we would say no variables were eliminated. And this just isn't a good option. Like, this wasn't a good way to try to solve this equation. Even if you tried the other option, which would be to subtract them or to change the second one into, multiplying it by a negative, 2x take away 3x would be -x, y take away -y would be plus 3y, and 10 take away 1 would be 9, and we still would not eliminate a variable. Is 2x plus y equals 10 equivalent to 4x plus 2y equals 20? That is, do they have the same solutions? Will their graphs be the same? So if I were to take the original equation and multiply the whole left side by 2 and multiply the whole right side by 2, I would get 4x plus 2y equals 20, and we would say, yes, that new equation, 4x plus 2y equals 20, is equivalent to the first equation, because all I had to do was multiply the whole left side by 2 and multiply the whole right side by 2, and we've already talked about that strategy working. So can we use this new equation instead of the 2x plus y equals 10? So originally we had 2x plus y equals 10, and we had 3x minus 2y equals 1. All I did was copy from up here, copied them down, and we tried to combine them and it didn't work. Well, what if we multiplied the top equation by 2 and we did 4x plus 2y equals 20, and we combine that with 3x minus 2y equals 1? Hopefully you'll notice that now we've created a situation where elimination does work. So 4x and 3x make 7x. This now cancels, equals 21. and we're able to solve for x equals 3. And so, yes, this is going to work. We would also need to plug that back into one of the original equations and say 9 minus 2y equals 1 if I subtract 9 from both sides. Negative 8, divide by negative 2, y equals 4. I get x equals 3, y equals 4. And just so you are confident that this does work, if we plug it in and we do 2 times 3 plus 4, we get 6 plus 4, which is 10. If we do 3 times 3 minus 2 times 4, we would get 9 minus 8, which is in fact 1. So if we plug this solution in, 3 comma 4, it does work in both of the originals. So that's another great option. So first we were just trying to add the equations together, didn't work. We tried to subtract the equations, didn't work. But if we multiply one of the equations, both sides, by a number, we can then create an equivalent equation that would work in the system of equations for the elimination method. There are 21 animals on Farmer Cole's farm, all sheep and chickens. If the animals have a total of 56 legs, how many of each type of animal lives on the farm? Write a system of equations. So we have two totals, right? We have a total number of animals and a total number of legs. That's going to be our two separate equations. So the sheep plus the chickens have to equal 21. Well, we have to know how many legs are on a sheep. A sheep has 4 legs, so 4s plus, and a chicken has 2 legs, so plus 2c equals the total number of legs, 56. So our first equation is total number of animals, second equation, total number of legs. If we tried right now to add or subtract these two equations, we would not eliminate anything. However, if we multiplied the first equation by negative 2, so if we multiplied everything in the first equation by negative 2, we would get negative 2s minus 2c equals negative 42. Our second equation would not change because we did not do anything to it. And now you can see we've created a system of equations where elimination works. So here we would get 2s equals the 42, which is negative, with the 56 is 14, and divide both sides by 2, we get s equals 7. So we would say 7 sheep, and we would have to plug that 7, right? 7 plus c equals 21, minus 7 from both sides, c equals 14, and 14 chickens. And if we did want to just double check, we can. 4 times, and we think it's 7 sheep, plus 2 times, and we think it's 14 chickens. Do we get 56? This would be 28 plus 28, which does in fact equal 56. So we can always check our solutions to these, which is great. It's great to be able to go back and check. All right. Now, this is another one where we had talked before about using distance equals rate times time, that it was going to come back. And this case, we are talking about the current of a river. So the idea of traveling upstream versus traveling downstream. While Brendan is vacationing with his family at the cabin, they take a motorboat on the river. The motorboat travels 18 miles per hour in still water. So we know that the rate in still water is 18 miles per hour. That's going to be really important because we're going to need that multiple times. We also need to remember distance equals rate times time is our general equation. Let W equal the speed of the river current in miles per hour. So that's actually a let statement. We don't want to forget that. They've told us to use W to represent the speed of the river current. Write an expression for how fast the motorboat is able to go downstream with the current, and another for how fast it can go upstream against the current. So if it's going downstream, it's going to go, it's 18 plus whatever the current of the river is. If it's going upstream, it's going to go 18, but you're going to have to take away the current because you're going to be going against the current. So those are the two expressions we need for if the boat's going downstream or if the boat is going upstream. Always important to write that down to keep yourself organized for when you want to actually write a real equation. The motorboat travels 49 miles upstream in the same time it takes to travel 77 miles downstream. So we're going to be using T equals time, which is pretty straightforward. What is the speed of the current? What is W? So let's break this into two separate equations. So 18 minus W is the upstream. So the motorboat travels 49 miles upstream in the same time it takes to travel 77 miles downstream. All right, so distance equals rate times time. Let's tackle the upstream first. Distance 49. The motorboat travels 49 miles upstream. So our rate is going to be upstream 18 minus W and T, whatever T is. And then we've also got the second equation, which is 77 is our distance. Our rate is 18 plus W because we're going downstream with the current T. First thing I would suggest, because these are not going to be friendly for doing the elimination method, is to distribute. So 18T plus, minus WT. And then this one's going to be 77 equals 18T plus WT. And the reason for that setup, notice one is minus WT, the other one is plus WT. All right, so we've got an equation for upstream, and we've got an equation for downstream. And let's see if we can combine those. So 49 equals 18T minus WT, 77 equals 18T plus WT, and here is the part that gets eliminated. When we add them together, the 77 and the 49 is 126 equals 36T. Divide both sides by 36, and we get 3.5 equals T. So if we want them to travel the same amount of time, and it's going 49 miles upstream, 77 miles downstream, it will take 3.5 hours to do both of those scenarios. So T equals 3.5. So that's only part of the question. It says, what is the speed of the current W? So time is great to know, but we're going to use that to find W. So 49 equals 18 times 3.5 minus W times 3.5. We could also do 77 equals 18 times 3.5 plus W times 3.5. It doesn't matter which one you substitute it back into. They're both going to work. So I'm going to do 49 equals 18 times 3.5 is 63 minus 3.5W. So I'm going to take away 63 from both sides. 49 take away 63 is negative 14. Negative 3.5, which is good because we want that negative divided by the negative to get rid of it. So 14 divided by negative 3.5 is 4. So according to that equation, W is 4. According to this equation, if you chose to substitute the other one, 77 equals 63 plus 3.5W. Take away the 63 from both sides. And luckily, or the way we would expect, we would get 14 equals 3.5W. Divide both sides by 3.5. Since they're both positive, 4 equals W. Shouldn't have mattered. You didn't have to do both. You were picking one or the other. In both cases, as it should, W came out to be 4. So if we look back up here, let W represent the river current. So W equals 4. The current is 4 miles per hour. And the other part of the answer is that these two boats were both traveling for 3.5 hours, but that's not really what the question was asking for. But you can always go back and put that in. All right, the only thing left on the page there is just sort of a cheat sheet or like a reminder, what would be the best methods to use and why. So equal values, anytime they're both set equal to the same letter. It doesn't necessarily have to be Y, but they both start with the same letter and an equal sign, or they both end with the same letter after the equal sign. Substitution, if only one of them has a variable that's all by itself, you can substitute the first equation into the second equation. And anytime it works, elimination method is always a great one to tackle. Here, this one's already set up for the elimination method. The second one, you could subtract in order for the elimination method to work. And then the last one, it says multiply both equations to eliminate one variable. When nothing else works, in this case, you could multiply the first equation by 3, and you could multiply the second equation by negative 2, And what they're trying to accomplish is they're trying to get rid of the x coordinates. So the first equation would become 6x minus 15y equals 9. The second equation would become negative 6x minus 4y equals negative 14. And you would be able to then eliminate the term with the x. All right, so lots of stuff going on in here. First is, the idea that you can multiply an entire equation to force the elimination method to work. And the second really big thing here is the idea of current. This example would also work if you were flying and you were going into a headwind versus having a tailwind. Same scenario, same way to solve it. All right, talk to you in class.